Hello guys again, and indeed I will tell you how to turn your, well, .NET software into computer chips. And let's start. I'm from a company called Lombik, just as a bit of interaction. As we have already discussed, I'm from Hungary, Budapest, but actually most of our clients are either from Western Europe or from North America, including companies like Microsoft or institutes like the Smithsonian Institution. Because day to day, we are providing software services, software development services for .NET and the web. Primarily, we work with an open source ASP.NET MVC web CMS called Orchard. So if you are working in the web sphere with .NET and you haven't heard of Orchard, I encourage you to check it out. It's a pretty cool CMS. But when we are not doing .NET Web, then we are doing some other cool stuff with .NET, well, including Haslier. Now, before we go any further, just a word of warning. Haslier works pretty well. It has some nice results, but it's not really ready for its prime time yet. It's not ready for production level workloads yet. You can still play with it, still evaluate it, but we are working it ready for bigger workloads with faster devices. What we are working on and what the current issue is, I will tell you a bit later. Sorry. So, to begin with, what is Haslier? Well, it's a tool that takes a computer program and turns it into a piece of logic hardware, so a computer chip. To be a bit more specific, what Haslier actually does is that it takes some logic, which is expressed as software form, and creates an equivalent logic, which is expressed as hardware form. So the logic stays the same, the algorithm it stays the same, the results that it computes stay the same, but before you had software, and now you have a piece of hardware. And all this magic happens with devices called FPGAs. Just a quick survey. Who has worked with FPGAs here before? Nobody yet. Okay, that's great, because then everything here will be new to you. FPGAs, or field programmable gate arrays, are basically computer chips that can behave like any other computer chip. So if you take an FPGA, then you can rewire it to behave like an old Intel CPU, for example, or you can wire it to behave like a computer vision chip. It's quite fun. Even though you haven't worked with FPGAs, I'm pretty sure you use them in one way or another. Because, for example, if you Google something on Bing, so to say, you have already used FPGAs, because Bing is accelerated by FPGAs. Azure also has FPGAs in every new machines out there, although they are not yet publicly available, and they just handle networking tasks to support the platform itself. But FPGAs are sometimes even found in household appliances like routers. Or if you went to a doctor and got an X-ray or a PET or an MRI scan, then those machines commonly had FPGAs as well. And also the fashionable topic of autonomous vehicles, self-driving cars, is not without FPGAs either, because those machines commonly have them for certain computing tasks. Since with FPGAs is basically chip design, a logic hardware design, you need to be a hardware engineer to use them. To give you a bit of an overview in totally non-scientific, very crude terms of the different merits of different computing devices, let's have some charts here. So let's compare CPUs and GPUs in video cards and FPGAs. First about parallelism, the chart on the left. CPUs in blue are on the lower end here, because a desktop CPU probably has 4 or 8 physical cores, maybe twice as many logical cores, but that's about it. Server CPUs have 32, 64 cores. GPUs in orange, on the other hand, are on the other extreme. GPUs are highly parallel devices with thousands of little processing cores even. Well, FPGAs in gray are kind of in the middle. FPGAs don't really have cores, so to say, but the level of parallelism you can achieve on an FPGA is somewhere in the middle, in the order of hundreds, sometimes thousands. Now, what about the complexity of programs you can run on such devices? Well, on CPUs you can run pretty much anything as long as it's software, even if not directly. So we are good there. On GPUs, the case is much more limited. You can't use every control structure even, you can't use just any data structure. There are some limitations. FPGAs are kind of a middle ground again. Although you can't really program an FPGA, but if you take a high-level tool like Heslier, you can create a program and turn it into an FPGA implementation, and in that case, the limitations will be somewhere in the middle. Now, power efficiency, however, the chart on the right is where FPGAs really shine. GPUs and CPUs are roughly on the same level here, depending highly on the specific application and the specific chip, but FPGAs can be very power efficient. And the reason is because you can configure an FPGA to just do what your application needs to be computed. It won't do anything else. There won't be an instruction set to handle. There won't be an operating system or other programs to run. It will just do what you need it to do. And that way, it can do much more per watt than CPUs and GPUs that are generic computing devices. But there is a big downside, and that is that it's, well, hardware engineering, and hardware engineering, how the name also applies, is hard. Programming a CPUs is easy enough. Programming GPUs is a bit harder, but you can manage. But utilizing FPGAs requires a completely different mindset. You need to think in hardware terms, in terms of wires and logic gates and clock cycles. It's totally different than writing a program. Well, but with high-level tools like Heslier, we intend to bring this level of complexity down onto the same level as CPU programming. So, to get back to our train of thought, what Heslier actually does is that takes a computer program and creates an equivalent FPGA logic. And obviously not just any computer program, but .NET programs. And what Heslier actually processes are .NET assemblies, the intermediate language DLLs. And that means that, at least in theory, not just programs written in C# or Visual Basic, but even other .NET compatible languages can be used. Heck, even scripting languages like PHP. All right, but why on earth are we doing this? And the reason is, of course, to get the benefits of FPGAs. So if your application, if the core algorithm of your application is massively parallelizable and is compute bound, so CPU bound, then with FPGAs you can get a substantial performance increase. And at the same time, you can have this with a higher power efficiency. So you can do more stuff with less electrical power. And this matters really if you are thinking of applications that potentially run on hundreds or thousands of computers. And with high-level tools like Heslier, this can still be software development as usual. So, a lot of talk until now. Let's have a quick demo. What I have here is, as the name also suggests, a parallel algorithm. And this code here, I will be able to turn into hardware with Heslier. This is, by the way, just standard C# here, nothing fancy. There are limitations on what you can do with Heslier, of course, but your code can be even more complex than this. Well, and what this algorithm does is that it takes an input number and then starts tasks. Tasks, as in the .NET Task Parallel library, are a bit like an abstraction over threads. If you start a task, then two tasks can be executed concurrently, and the level of concurrency will depend on the capabilities of the platform the software is running on. My machine here has an Intel i7 CPU with 4 physical, 8 logical cores, so that will be the hardware level parallelism. But here we are actually starting 280 tasks. And if we turn this into hardware, then on the hardware, on the FPGA, there will be actually 280 independently running little processing cores. So on the hardware, we will get an actual hardware level parallelism of 280. And in these tasks, we do a bit of conditional logic that we run 10 million times. And then the result is returned back. Then we wait all of these tasks to be finished. And once that happens, we sum the outputs. And this sum will then be the output of our whole algorithm. By the way, this example is up on GitHub, which I will show the link to a bit later, so you can check all of this out in detail. And there are many more examples too, of course. So I will now run this application, which is part of a small console app. And I have an FPGA prepared here. I'm now showing this to the webcam, so I hope you can still see it. This is a relatively cheap $300 low-end FPGA development board that I have prepared here. It's an Nexus 4 DDR that you can buy fairly easily. It's not fast, but it was fairly easy to start with, so we started developing Haslier with it. Now, in the background, Haslier created the hardware implementation and has executed it on the FPGA 3 times. And all 3 times, as you can see, it took about 300 milliseconds. Actually, if you take a closer look, it took exactly the same amount of time. And the reason is that on the FPGA, again, it's just doing what you need it to do. There are no noisy neighbors, no other programs to run, so the execution time is deterministic. And if you also take the communication round trip with the host PC into account, it was just below 400 milliseconds. The difference is here is also because this is a relatively slow board, and it connects via an also relatively slow virtual serial communication channel to the host PC. We are also working on supporting higher end, faster, bigger boards, and that would mean that the communication there will be faster as well, using channels like PCI Express, for example. But even with the slow board, it's much faster than on the CPU. On the CPU here, it took about 5 seconds compared to the 300 milliseconds. So there is a factor of 10 difference, how much faster the FPGA was. Now, obviously, my CPU is doing a lot of things here. I'm screen sharing and everything. But even if it would be idle, it would take around 2 seconds on the CPU. So still about 5 times slower than on this cheap low-end FPGA board. So this should give you an idea of what's possible with Haslier. So let's wrap up. What are we doing with Haslier? Because just this is just the current state. We are of course not stopping here. Well, first of all, we are working on field testing Haslier to get more real-life use cases because we are not there yet. We are also making Haslier high-performance computing ready. As mentioned, we only support this low-end board currently, but we are working on supporting bigger boards where you can put actual real-life production-level workloads there. And it seems that FPGAs are coming into every data center out there. AWS, the Amazon cloud, already has FPGAs publicly available. As mentioned, Azure has FPGAs, although they are not yet publicly available. I would presume they soon will be. And Intel is betting on FPGAs as well. They acquired the then second largest FPGA manufacturer, Altera, 2 years ago, and now Intel is an FPGA manufacturer. And they are working on bringing FPGAs and their CPUs together, like they are working on a Xeon processor that is packaged together with an FPGA. All right, if you like this, you can start by checking out the SDK that's up on GitHub as mentioned, and be ready because it seems that FPGAs are coming. So if you remember a few years ago, the case GPUs, they were kind of a curiosity too. But nowadays, GPUs are just another computing device that pretty much everybody can program. program. I think we are in the same case with FPGAs. But soon enough, with FPGAs, you will have another computing device to choose from. So that was it for the lightning talk. Thank you for your attention. If you have a use case for if you have a use case for Haslier, just get in touch with me via email. I will be happy to discuss. Otherwise, there's Haslier.com for any other info. As mentioned, Haslier SDK is up on GitHub. You can use it for free. And if you are interested in the curious people behind Haslier, check out onbit.com. And now we can have a little bit of discussion if you are interested. I will be happy to answer any questions you may have.
Bitcoin miner. So Bitcoin.
That's what I was going to say.
Everyone's going on. Hi, Zoltán. So it's Bitcoin miner.
Hello.
Is that a question you asked?
Yeah, Bitcoin, is it fast enough to build a Bitcoin miner?
That's a good question. The short answer is not anymore. FPGAs are not competitive anymore for Bitcoin mining. They were for a short period of time, but nowadays they have dedicated chips just for Bitcoin mining, and they even exaggerate the benefits of FPGAs because dedicated chips can be even more faster and more power efficient, of course. But that being said, it's interesting to see how FPGAs and Haslier could be used for other cryptocurrency mining. And we even have had inquiries about that. Though some people are testing Haslier for mining Ethereum, for example, I have heard. But since other people are using FPGAs to mine Monero, I think, and Zcash probably, it would be interesting to see how Haslier can compete there.
I have two questions, please. One is,
sure.
What can't they do? And do you know if Intel plans to integrate the FPGAs with the CPU so you can share CPU cache?
Could you please repeat the first question? I couldn't quite get it.
Yeah, what can't FPGAs do? As you said that they can do most sorts of generic tasks, and you can't transpile like any kind of stuff. So what are the limitations?
All right, thanks. I got the questions. So as for the first one, what are the limitations? First of all, an FPGA is not doesn't have a limitless area. So simply what you can fit, what kind of logic you can fit there has limits. This highly depends on the FPGA itself and highly depends on the complexity of your application. As you can see, we can get 280 copies of this simple algorithm to this low-end FPGA. But the higher-end FPGAs have 20 or 50 times more capacity than this FPGA I have here. Again, this highly depends on the FPGA and your application, but this probably gives you an idea. As for bringing together a CPU and an FPGA, Intel is working on that specifically. That's what I mentioned. They have currently a Xeon and an FPGA on the same chip, in the same package. And they are working on having them on the same die, on the same piece of silicon. So basically, you will have an FPGA core on the CPU. And in that case, the FPGA will share the same, probably even the same CPU caches than the CPU cores. They had some talks about that, but as of lately, there are no news there. And the other FPGA manufacturer called Xilinx is, I think, also working on something like this. What are commercially available for a long time are systems where there is an ARM CPU and an FPGA on the same board. So not very close yet, but at least on the same board.
Thanks.
Any more questions?
So have you done any work with neural networks like TensorFlow or Keras or anything? And because it seems like it would be a good application.
So about neural networks, if I understood correctly. That's also a very good question. Not yet. We haven't tested enough Haslier yet. We are currently working on it. And indeed, neural networks and generally machine learning and artificial intelligence applications are something suitable for FPGAs. So there are teams using FPGAs for these tasks, just not Haslier yet. And since you also touched on TensorFlow, what we are also evaluating is accelerating pieces of TensorFlow with Haslier, like if there is some quite compute-intensive subpart of TensorFlow that we can substitute with a simple enough .NET implementation, and then we can hook this up into the TensorFlow pipeline. We'll see what this will bring. We are evaluating what to do there. We haven't done anything yet, but since people have been evaluating FPGAs generally for the same tasks, that's also something promising.
There is the Google TensorFlow processing unit, the TPU FPGA. So what was the question again? I think Google developed a chip for the TensorFlow. This is the TPU. Is that the FPGA or not?
No, it's not.
It's not.
I don't know much about it. Just read out a few articles about it in the news. But as far as I know, it's a standard hardware chip. So they basically gone a step further and created a hardwired dedicated chip for that. That's of course even better. The difference here is that you can get an FPGA implementation with the costs of an FPGA, which in this case is $300 US, but for higher end FPGAs it's a few $1,000s, and the cost of using Haslier, so basically creating a .NET implementation. Now there are other high-level tools comparable to Haslier too, where you can also just run a program and create an FPGA implementation. So that's the cost of having an FPGA implementation, while the cost of creating a dedicated chip is much higher. You need millions of dollars to begin with and a much longer time because you need to test the chip very differently, and there is the actual manufacturing as well. So that is only feasible if you are a company like Google and you are creating a chip for a software like TensorFlow.
Another question. Are you able to recompile your program, or it's like just worked once?
So could you say?
Are you able to recompile your program, or it's just one time off?
I'm not sure I entirely understand this. Yes, you can. Yes, you can. So an FPGA you can reconfigure pretty much anytime. So if you change something in your program, you can convert it again with Haslier, and you can configure the FPGA again. So you can just keep on developing your software, keep on reconfiguring the FPGA with other software. It will just work.
Last question here. Okay, you have a question?
It was a similar one, but just to expand to that, can you have like multiple configurations? For instance, you have multiple applications that uses the same chip. Then you have a little different scenarios.
Yeah. Well, with Haslier you can't. Well, let me elaborate on that. With Haslier, you can have a single application being configured for a single FPGA. In that application, you can have application level parallelism or task level parallelism, as I mentioned, and in there you can have any number of methods, any number of classes. So it can be more complex like this, but generally there can be a single application configured in the FPGA. That being said, you can have multiple FPGAs connected to the PC, or we also support Ethernet network communication, so you can also connect it to a network switch or something. And if you have multiple FPGAs, you can have different applications running on them, Or you can have the same application on every FPGA, and then you can get device-level parallelism too, because you can have a little FPGA cluster where all of the FPGAs are doing the same thing, and that way Hasslier will be able to distribute load among them.
I think that's it. Thank you very much, Zoltán.
Good. Thank you very much.